continuous motion in space. I want to find the maximum range for a projectile. What did we get as the range last time?
It was V naught square sine 2 theta divided by G.
V naught was the launch speed, right? And theta is our launch angle. But we have two variables here, right? We have speed and we have angle. However, in most cases, you only have control over one of those two. That's the angle, right? And generally speaking, your speed is fixed. In the firearms, it's called the muzzle velocity. That's fixed for the firearm. You can't really change that. How do we maximize a function? Back to Cap 1. Or what? This is where the function equals 0 or where the function would be undefined. When doing the maximum, yes, of course, obviously the, no, I lied, it could be undefined. Derivative could be undefined because all that matters is the function defined at that point. Well, what are we going to take the derivative with respect to here? The theta, right? It's the only thing we can control. What's that derivative? You have one too many terms. What are we differentiating with respect to? It's that second one, right? and V naught as a constant. And V naught not a function of theta.
Wait, why did we got the 2 from the 1 in the front? The V naught 2. Yeah.
This one here?
Yeah.
It's the derivative sine of 2 theta. You have to use chain rule, right? So the 2 came from the derivative of 2 theta. Is there anywhere that derivative is undefined? No, right? It's defined everywhere. So set equal to 0, solve for theta. Means cosine of 2 theta would have to be 0. What are all the possible values for 2 theta? So where's cosine 0? What angles make cosine 0?
Pi over 2
Where else?
and 3 pi over 2 and any number in the form pi over 2 plus n pi or n is good.
Yeah, how about that? I'm going to write it a different way. But yeah, that's right. Odd multiples of pi over 2. What does it mean that theta would be any odd multiple of pi over 4? But let's think about this. What is the domain for our range?
0 over pi over 2.
Why?
Isn't that the range for the theta?
Why would it only be those values though? You're right. I'm asking why. How'd you get it?
I just imagine like how the projectile is launched, and it would be like on that plane.
Not going to launch it downwards, right? That wouldn't make any sense. So straight ahead would be 0. You could theoretically launch it straight up. That'd be pi over 2. If you launch it backwards, you just reorient your coordinate system, wouldn't you? So we're on that's forwards between 0 and pi over 2. So realistically speaking, our range of values for theta are just 0 to pi over 2. Of these infinite number of solutions for theta, which ones are between 0 and pi over 2? So which odd multiples of pi over 4 lie between 0 and pi over 2? Is that an odd multiple of pi over 4? Just pi over 4, right? We only get one critical value. Now we have the critical points. What did you have to do next? Well, we're trying to find the maximum. So what was the point of finding that value?
You plug it back into the original function.
You have to do something first. So extreme values would occur at critical points, right? Critical points or endpoints. Is that guaranteed to be a maximum? All right. It could be a minimum. There's a few things you could do. You could plug in all 3 values to the original range and find out which is the largest. You could set up your test intervals. If it goes from increasing to decreasing, it's a max. Decreasing to increasing would be a min. Typically with optimization problems, what you do is we use the second derivative test. Specifically the corollary to the second derivative test, which states if C is your only critical point, then the second derivative test gives you absolute extrema instead of local extrema. What's that second derivative? was negative 4 v naught squared what? Two times pi over 4 is pi over 2. Sine of pi over 2, positive or negative? V naught squared is positive. What's G?
It's positive.
G is also positive. So what do we have? We have negative times positive is negative, divided by positive is. Second derivative is negative. The corollary to the second derivative test states that our critical point results in an absolute maximum. So we know that point is the maximum. Now plug it into range. What is sine of pi over 2?
One.
Maximum range of projectiles v naught squared over g. So if you want to maximize your range, you want a launch angle of 45 degrees. We made a major assumption though.
The projectile isn't moving close to the speed of light. Distortion.
Well, that's very true. Once we have to start taking relativistic effects into it, things change. That's not the assumption I'm referring to, though. I mean, let's be honest. If our projectile is going at the speed of light, I don't think we have to worry about the range at all.
Intergalactic warfare.
There. You have other things to worry about at that point, like crap, we're being invaded. There's another major assumption that we're making, and it's a very fatal assumption too.
That it is logic from the ground.
The analysis would be the same regardless, because of how we can set the coordinate system. We're assuming there's negligible air resistance. We're ignoring drag. Our projectile motion model ignores drag altogether. you have air resistance, the model becomes a lot more complicated. I'll save that for a classical Newtonian mechanics class. Projectile is launched at a speed 500 feet per second at an angle 45 degrees to the horizontal. Determine speed and direction after 5 seconds of flight. Position would be given by this. What is cosine of 45 degrees?
Square root 2 over 2.
What is sine of 45 degrees?
Square root 2 over 2.
I'm leaving that G alone for now. We want speed and direction. Which means first, we're going to need V. We're going to need velocity. Direct that when V is, or when T is 5. So after 5 seconds, that would be the projectile's velocity vector. Well, speed is just that magnitude, right? Make things simple. There's a 5 common. Factor it out. What's 250 over 5? 50. What's 50 squared? Times 2. $50 root 2 times G times 2. And then just plus G squared.
I'm sorry, can you just explain how you got that 100 square root of 2g plus g squared again?
Factor 5 out of the second term and square. Right, so it's 50 root 2 minus g, all squared. That is the speed. So let me just write up here the approximation. If we approximate this using g is about 32 feet per second and keep it to no decimal places, should find it's about 403 feet per second. For direction, I'm going to use phi to represent the direction. So tangent of phi would be the y component of velocity divided by the x component of velocity. Direction is going to be between 0 and pi over 2 as well, right? No. Negative pi over 2 to pi over 2. Right, because it could start to drop. Which is the range of the inverse tangent. So just take the inverse tangent of both sides, that's your direction. You should find that to be about 28.7 degrees. Point is moving along a circle of radius r. It's moving with constant speed. We're going to show that if the radius vector to p moves with angular velocity omega and angular acceleration alpha, then speed is radius times omega, and acceleration is radius times the square root omega to the 4th plus alpha squared. velocity is derivative of position. What is the derivative of r cosine theta? It's like you're missing something now. Theta is a function of time, isn't it? So you have to use chain rule. The theta dot, derivative of theta with respect to time. Right, that's change in angular position with respect to time, which would be angular velocity, wouldn't it? There's our velocity vector. Well, acceleration is the derivative of that. Is the radius a function of time? So does r change with time? No, right? It's a circle. That's good. R is constant. Omega. Angular speed. Does that change with time? Yes, it does. Does sine of theta change with time? It does. Again, your angular position is changing because your point's moving along the circle, so your theta is changing. That's a product rule. And same reasoning. For your second component, it's a product rule. Again, theta dot is just omega, but omega dot, change in angular speed with respect to time. Angular acceleration, right? There's our two vectors, velocity and acceleration. We just have to find the magnitude of each one now. Well, notice in velocity vector you have r common, factor it out. So you have r times square root of your first component squared plus second component squared. What's under that square root is just omega squared. But omega is angular speed, which is always non-negative. So the square root of omega squared is just omega. And we get r omega. Acceleration also has an r in common, factor it out. This one is going to be a bit of a pain. And for the sake of time, I think what I'm going to do is let you do a lot of the algebra. So I'm just going to skip to this step. So after some algebra, you're going to get to this. Omega to the fourth times cosine squared plus sine squared plus alpha squared times sine squared plus cosine squared. Just r times the square root of omega to the fourth plus alpha squared. As desired. Again, I'll leave that algebra to you. Now we move on. We now look at multivariate calculus. So we're done with vectors. What we do now is the study of multivariate functions. Right? Every function we've worked with up to this point has been what's called single variate. Right? F of x, h of t. You've had one independent variable. But that's not really realistic. Even something as simple as volume. Actually, area. Area of rectangle. Depends on length and width, right? That's a two-variate function. You have two independent variables, length and width. Volume. So volume of a box, let's call it. Length times width times height. Or length times depth times height. It's a three-variate function. We restrict our study, for the most part, to two-variate and three-variate. Function of two variables is any function z equals f of x, y. It maps each ordered pair x comma y to a unique real number z. So it maps an ordered pair in the real plane, R2, to some real number, z. So maps R2 to R. Domain is now a set of ordered pairs. It's not a set of numbers. So domain is now a set of ordered pairs in a plane, which is a region. And the range is still a set of numbers. So here's what a two-variate function is doing, right? Takes a point in a region and maps it to a point on the number line. By the way, when you plot a single variate function, how many dimensions is it?
2.
2, right? X and Y. So what happens if you plot a two-variate function? You went too high. It's 3. You're 2 independent plus you're 1 dependent. Here. Sketching single variate graphs was hard enough. Sketching a 3-variate graph. I'm not doing it. But there are several ways to examine what that object would look like. One is to use level curves. Given a function f of x, y, a number c in the range of f, level curve of f for the value c is defined to be the set of points that satisfy that equation, f of x, y equals c. The plot of all of these level curves is called a contour map. And you're familiar with contour maps. If ever looked at topographical map, they use contour, they use level curves for altitude. Right. Also, some temperature maps have temperature differentials, I think they're called. Those are, again, level curves for different temperatures. Right, then you also have the vertical trace, which for the sake of time, I'll let you read that on your own. Three variant functions. Any functions of the form w equals f of x, y, z. Right? So now what we're doing is I'm taking an ordered triple in space, right, R3, and mapping it to a single real number w. Domain is now set of ordered triples, so it's a what we call a solid. And again, the range is just real number line. It's a set of numbers. So now we just take a point and a solid, map it to the real number line. Graph of a three-variate function would be how many dimensions?
Is it 3?
It's 4. Good luck. Your coordinate system would now have to include a fourth axis that is perpendicular to x, y, and z. In other words, it would have to extend out into the fourth spatial dimension, which we can't do. We can't even visualize what that would look like. So we're just simple three-dimensional beings. Want a good illustration of this? Read the novel Flatland. Does a really good job of trying to describe what higher dimensional space would be like. You're physics, right?
I'm math.
You're pure math, I thought you were physics. I'm going to change it to physics so you have to deal with it. Because it is a pain in the ass to deal with. Math, you'll never deal with it.
Higher dimensions.
Yeah, you don't really deal with higher dimensions.
Well, I guess it depends on how you.
Even if you take college geometry, I think it just sticks with 3 dimensions. Yeah, I can't remember ever doing anything above 3 dimensions in my math studies. Outside of this. Even topology was not really higher dimensions.
4-dimensional topology sounds awful.
No, just no. Just no. If someone asked me if I wanted to take topology in 4 dimensions, you couldn't pay me enough to do that. Of course, we have level surfaces. Same concept as a level curve. We are going to have to, speaking of topology, we are going to have to deal with some basic topology. First, the idea of a delta disk. So consider an ordered pair in the real plane. A delta disk centered at the point AB is defined to be an open disk of radius delta centered at AB. In other words, your delta disk is that set. And then if you plot it, this is what you'd have. Close to what you would have. They made a mistake in this. That's supposed to be dashed, not a solid line, because it's open disk. So consider a subset of the real plane. Point P naught is called an interior point of that subset S if there is a delta disk centered around P naught contained completely in S. The point would be a boundary point of F if every delta disk centered at P naught contains points both in and out of S. So that is a really fancy way of saying this. Draw out your set. Interior points lie within the boundary. They actually lie in your curve, in your region. And boundary points are just what they sound like. They lie on the border of the curve. Right. So this is interior. Right, you can draw a delta disk centered around it that's contained entirely in S. That would be a boundary point because no matter how small you make that delta disk, it's always going to be both inside and outside of your set. Again, consider a subset of the real plane. And by the way, yes, I am only looking at the real plane here, but this notion extends to any dimension. Right, so these definitions are the same regardless of whether it's the real plane, real space, real force space, so on and so forth. We say S is an open set if every point of S is an interior point. It's a closed set if it contains all its boundary points. So question. Does every set have to be either open or closed? Could be neither. There's a set neither open nor closed. It doesn't contain only interior points, but it doesn't contain all the boundary points. So an open set is connected if it cannot be represented as the union of two or more disjoint non-empty open subsets. Generally speaking, that means that your set is not overlapping. And we call the set a region if it is open, connected, and non-empty. Two-variate limits. This is where the fun begins. Here's the official definition, the formal definition. Let f be a function of two variables. Limit of f of xy as xy approaches the point a, b is L, written that way. That's not centered, so that's bothering me. If for each epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of f of xy minus L is less than epsilon, whenever the square root of the quantity x minus a squared plus quantity y minus b squared, that squared should be on the outside, is less than delta. One of those I can't fix. This is just kind of visualizing what the definition says. Right, so we can make F arbitrarily close to L by choosing a sufficient delta disk, or a sufficiently small delta disk around AB. The limit laws. That should be fixed as well. All right, so limit of F is L, limit of G is M, C is a constant. Limit of the constant is a constant. All right, so that's still the same. I have to fix it for all of them. That's annoying. Limit of X is just A. So if it's just a single variate function you take the limit of, it acts as a single variate limit. Same with limit of Y. Those are your two identity laws. You still have your sum and difference laws. Right? Limit of sum or difference is the sum or difference of the limits. So I have the scalar multiple law. If you have a scalar multiple, you can pull that scalar outside of the limit. So you have your product law. Limit of product is the product of limits. So you have your quotient law. Limit of a quotient is the quotient of the limits, as long as the limit of the denominator is not 0. Still have your power law. Still have your root law from Calc 1. Right? And definition for continuity is the same. And all of those that we just went over can be extended to higher than 2 variate. And the definitions are pretty much the same. You just have to account for that new variable. Limits in Calc 1. They weren't too bad, were they? 2 variate limits are a pain in the ass. As are 3 variate limits. Single variate limits, how many directions could you approach your value from?
2.
Left to right, right? Go to 2 variate.
Infinite.
Yep. Can't you approach an ordered pair an infinite number of ways? And keep in mind, they also don't have to be straight lines. You can approach it in a curve as well. The limit would exist if and only if the limit from all possible paths are the same. So in that sense, if you can find two paths that give you different limits, your Young limit does not exist. But at the same time, you can't do, say, 10 paths, get the same limit in each of those times, and then conclude that the limit exists. So generally speaking, taking a two-variate limit is a massive pain. Three-variate's even worse. But have no fear, because I think we're going to be doing, at the very least, two-variate limits. Do I have any three-variate? No, I don't. But we'll be doing a bunch of two-variate limits. But that will be for next time, which is tomorrow. Second project, which is the proof of Kepler's laws, is due tomorrow. Homework 10.
Isn't there a quiz that's due opens on 28th and due?
Yeah, it'll open tomorrow.
Oh, okay.
So I'll discuss it then. The 10th homework on web science should definitely be up by now. I think I put a typo last time on the due date. What did I have it set at? The 4th? I think on Tuesday. The slide said the 4th. It's actually due the 6th. So that's due next Thursday. And homework 11, again, I don't remember when I started putting them up earlier, but that will be due next Friday. So that'll either be live now or will go up tomorrow. See you tomorrow.